everyone. My name is Ankit Istana, and I'm the program manager for the backend Visual C++ compiler, which means the optimizer, the linker, and a bunch of tools that we make. I'm here today to talk about the new Visual Studio 2013, and in particular about the Visual C++ backend compiler optimizations. So if you're interested in knowing more about how to make your code run faster, you should watch this video. So the first set of optimizations I'm going to be talking about are essentially free, and all you need to do is to compile your code or your application with O2 or Friends or whole program optimization to leverage them. So I'll move over about talking about these optimizations. For Visual Studio 2013, we've continued to improve the analysis performed by the Visual C++ compiler, so it can produce code that runs faster than before. I would like to highlight a couple of these optimizations in this slide. The first one is called permutation of perfect loop nest. So if you have a nested loop and you're processing large arrays, which are too big to fit within your processor's L3 cache, then the speed at which your code runs is most likely to be dominated by the time it takes to fetch from memory, rather than the actual calculation being performed inside the loop body. And sometimes by changing the order of the nested loops, we can make it run much faster. So let's take a look at this matrix multiply example here. And so this is a regular matrix multiply example that you've probably seen before. But if you take a look at the innermost loop here, and you take a look at the memory access patterns for the array B sub k sub j array element, then you will notice that it has actually very poor spatial locality. However, if you now flip the inner loops and then you actually take a look again at the spatial locality for the array element B sub k sub j, you will notice that there's a tremendous speed improvement because you've improved the spatial locality essentially. So with the Visual Studio 2013 Visual C++ compiler, some of these loop optimizations will be done automatically for you if it's functionally correct to do so. As I say on this slide, if the array elements or the number of elements in your are larger, or as n goes larger in this example, the amount of speed up that you'll get will increase as well. The next optimization that I want to talk about is all the vectorization work that we've done. So auto-vectorization is an optimization that was introduced in the Visual C++ 2012 compiler. And in Visual Studio 2013, or Visual C++ 2013, we've essentially added more smarts to it. So now we basically support a lot more operations that inside a loop body. So for example, if you were doing min-max types, or if you're doing conversions in a loop body before, we won't be able to vectorize it. But with the new compiler, we can now vectorize these things. Another example of the work that we've done is to support, or we actually now analyze the restrict keyword, which helps us essentially remove or elide runtime checks required for pointer overlapping. The last thing that I want to talk about here as well is, we've also introduced this technique for statement level vectorization, and you'll see an example for this in a couple of slides. So to illustrate my point about the work that we've done for the vectorizer, take a look at this example. In the first example, if you take a look at the loop body, we're doing a bunch of pointer arithmetic here. And with the new compiler, we can now vectorize this. Take also notice that in this example, we're not using a traditional counted for loop. Instead, we're using a while loop. So why is this important for you? Why is this important? Well, if you take further notice in that example, you'll see that this is actually a function from the STL library. So this code pattern is pretty common. The next example that I have here is basically from a machine vision library, and what's different about this example than a traditional example is that if you take a look at the loop body, we're now accessing the array using the box start as a start index, and in Visual Studio 2013 we're able to vectorize this as well. The next example that I want to talk about is statement label vectorization. So there's no loop. If you take a look at this example, there's no loop here. But the compiler recognizes that you're doing identical arithmetic, which is that you're taking the reciprocal of adjacent fields within a structure. And it's able to vectorize this code as well by making use of the processor's vector registers and instruction. So this is pretty cool. The next optimization that I want to talk about is called profile guide optimization. Profile guide optimization uses training data collected from running performance-centric scenarios to further optimize application performance. In Visual Studio 2013, we have introduced the capability to Pogoize Windows Store applications. So if you have a Windows Store application that's performance savvy, then you should use this optimization to benefit from it. Lastly, in VS 2013, we've also added smarts to Pogo, such that Pogo can now extract higher performance by being able to do better data and function layout. The next thing that I want to talk about is traditionally for folks that are experienced users of profile guide optimization. If you used Pogo before, you already know that the performance benefits that you will get with profile guide optimization are directly proportional to how well you train the application. So in VS 2013, we've added a feature which allows you to validate your training session for profile guide optimization. So now, if you take an F1 profile report, which is generated from your Pogoized application, you would see in the report that it contains additional information. Among other things, you'll see a column for whether a particular function was Pogoized or not. For example, if you take a look at the wmain function here, you will see that the isPogo field is set to yes, which means that this function was Pogoized. In addition to this, we also capture now whether the function was optimized for speed or size. So profile guide optimization would compile or optimize a particular function for size if it's cold, and it will optimize it for speed if it's hot. So having this extra piece of data is useful because now you can actually validate whether your training session went well or not, and whether it captures the performance-centric pieces of code. The next thing that I want to talk about is a new calling convention that we've introduced as a part of VS 2013. The new calling convention is called vector calling convention, and this convention is specifically to help when passing around vector type arguments. So if you're passing vector type arguments in a function call, we now basically use vector registers, XMM, YM, for example, for passing these arguments. This is traditionally much faster than other calling conventions like fastcall for x64, because A, it reduces the stack allocation, and B, it reduces the number of instructions to do the same. In addition to that, you'll see some code size footprint wins as well. So if you want to take a look at this convention and just want to see how much performance gains you'll get with this, you could actually use the /gv compiler option and validate whether vector calling convention is bringing you some wins or not. This should, as I said before, this should especially help if you're doing vector type math in your code. Using this convention is pretty simple. You basically decorate your function name with a vector call keyword, and that tells the compiler that you want to use the vector calling convention. Now, in this example here, the struct particle example, I'm showing vector types M256, but vector calling convention, it goes beyond this as well. So vector, as I said in the last slide, vector calling convention is not just about the vector types, but if you have a structure, for example, the HFA example in this box, vector calling convention, if you're passing the HFA example as a function parameter, we'll be able to use vector registers for this as well. We call this convention or notation homogeneous float aggregate data types. And vector calling convention helps here as well. The last thing I want to talk about is C++ AMP. So C++ AMP is relatively a new technology which was first introduced in Visual Studio 2012. It allows developers to express their data parallel algorithms using C++ STL-like code and achieve massive parallelism by automatically running the code in hardware specifically designed for execution of data parallel algorithms. Larger the data set, greater the performance improvements compared to CPU. C++ AMP offers you a variety of features. The key ones I would like to highlight here. It's very productive as it's simple. It has a simple programming model, which is STL-like. It's portable because it's hardware and platform agnostic support. And it's obviously performant because you can achieve massive parallelism by targeting data parallel hardware. In Visual Studio 2013, we've added these perks to C++ AMP. The data transfer between CPU and GPU on shared physical memory hardware is a lot more efficient now. We've actually enhanced our support for textures. And lastly, we've improved the C++ debugging experience. Thank you for watching my video. And if you want to learn more about the Visual C++ compiler or the C++ language in general, please visit our blog at VCblog. We would love to hear back from you.